to semantic solutions and curriculum complexity, curriculum vasca, and we start from the basics. My research focus is in how semantic solutions can contribute in curriculum analysis and evaluation. Today, we will discuss about two interesting papers that I read recently. The first three sections are talking about the first one, and the fourth one, which is the number 4 is not available, it's on the right. It's discussing about a preprint, a quite interesting preprint work. First one is about the curriculum mapping problem, a paper by Zuri and Fergon in 2021, which is talking about an ontology-based approach for curriculum mapping in higher education. Curriculum mapping is essential for quality assurance and industry alignment. Traditional mapping, the problem, what is the problem? The problem is that traditional mapping is static and highly time consuming. Zuri Fergon's work in 2022 is talking about using ontology-based approaches for curriculum mapping in higher education context. Curriculum mapping is essential, especially in higher education, for quality assurance and industry alignment. It happens at 3 levels: institutional, program, and course level. However, traditional mapping is a labor and time-intensive process. It also suffers from interpretation discrepancies between faculty. Zuri and Fenworth argue that by applying web ontology language, we can create a machinery that will share vocabulary. This way, we can cross curriculum mapping from a mere documentation task to an automated knowledge representation process. Essential as it is for quality assurance and industry alignment, it happens at 3 levels: institutional, program, and course level. No, I said that. And this comes from the curriculum from super wide. Here we go. Okay. The author's core contribution is the design of the foundational curriculum ontology, but rather than trying to model every edge case in academia, they strip the core domain of the curriculum down to 7 core concepts, such as program, course, unit, objective, learning outcomes, etc. They also define the object properties that represent the relationships between the classes, the concepts, actually, while data properties hold the actual attributes. The paper's value of insight is its framework for knowledge discovery. They propose a 3-layer architecture: the core curriculum layer, the middleware, and the top layer. We will see that in the next slide. And by establishing this architecture, individual institutions can more easily extend the ontology to their specific needs while maintaining a universally understood baseline. Here we see the core architecture of the framework, the 3-layer framework. On the bottom, we have the curriculum knowledge-based layer, where the core curriculum knowledge lies. Above it is the middleware layer, where the authors utilize SWRL as also its extension, SQWRL. SWRL allows the system to infer entirely new knowledge that wasn't explicitly stated simply by combining known facts, while its extension, SQWRL, used to retrieve and filter those facts from the ontology. And in the top layer, it's the user interface. To continue and to prove that in the practical application of this approach, the authors use a case, a quite common and modern case for ontology extension. The challenge is to include and adapt traditional rigid structures such as micro-credentials into the ontology. Thus, they introduce new concepts, micro-credential, task, theme, and track, and they extend the already have the core ontology and include that the concepts in there. And furthermore, they use SWRL to automatically identify existing course units that satisfy micro-credential objectives. For example, if a concept, or if a class includes the word, one particular word, then they build a micro-credential task and track it. The primary strength of this work is standardization and usability, since it successfully translates pedagogical goals into computational logic. However, there are also significant limitations. First, this work remains in conceptual design. The authors, by themselves, explicitly state that evaluating the system's actual reasoning capacity is future work. Second, the inference logic is currently quite simple. The rules rely on the exact string matching, like finding the word business, which ignores the semantic variability of how different professors or authors write syllabi. It's quite simple, that examples that they publish in their work. During third work, he built a robust structural foundation, but with the logical next phase of research is necessary building more ontologies. It is bridging the gap between raw data and this structured OR framework. And nowadays, we can use natural language processing or large language models to automatically extract learning objectives from structured and unstructured PDF text and map them to these objectives and object properties. And that is from the first paper. And now we pass and we continue to the second preprint paper, which I also found quite interesting and quite near to the first paper. That's why I choose to include it also. This paper, this work by Christopher et al. At 2025, they are talking about the distributed content problem. They suggest an ontology for representing curriculum and learning material and how to identify and represent it using an ontology. We turn now to a broader challenge. Educational learning and training materials have become extremely commonplace across all over the internet, but they still remain frequently fall into platform silos and remain disconnected from one another. Thus, it's difficult to connect them, to align them, and to reuse them. Greenstone and colleagues in their 2025 preprint propose a framework to overcome this fragmentation. They argue that integrating this massive amount of material requires providing structural cross-links across topics. They achieve this through the curriculum KG of ontology, a knowledge graph ontology which acts as a framework for the dense interlinking of educational materials by establishing organizational, and broad pedagogical principles. The core contribution of this work is the curriculum KG Ontology, which was designed by a specific overarching use case, the prototype Open Knowledge Network, so they reuse them. And to build this, the authors employed a modular design methodology. They isolate one core concept and its related concepts into distinct modules. This segmentation is crucial because it facilitates understanding and confines future modifications to simple modules, making the ontology highly reusable. In this framework, the top entity is the curriculum, which represents the comprehensive educational framework. Every curriculum must have at least one module to provide organized educational resources. Here we see the schema diagram from the overall curriculum KG ontology, where the yellow boxes indicate the classes, the purple ones are the controlled vocabulary, while the yellow ellipses indicate the data types tied to those classes. As you can see, we can see the curriculum, which is the core concept, and each curriculum must have at least one module. And from the module, all other concepts are linked. But where this paper gets really interesting for knowledge representation is its approach to personalized instruction. The ontology formally models audience-specific curriculum through a concept they call persona. A persona represents an abstract perspective or set of requirements for an individual learner. Each learner may have one persona. For example, distinct personas might consist of developers, enthusiasts, executives, contributors, and students, etc. To achieve this, they utilize the agent role pattern from the module library, establishing that a person can assume different roles, such as an author or a persona. These personas directly shape the architecture of the framework key concept, the learning path. And this path is not static, but it's a dynamic series of learning steps that maintains a continuous flow through specific properties like his next learning step or his previous learning step. To ensure that the ontology is useful and not just a theoretical exercise, Priestley et al. Provided a materialized knowledge graph for the proto-OKN use case. They also validated that graph and tested it against competency questions sourced directly from domain experts and education too. The authors also emphasize human readability for future ontology developers. They rely on detailed schema diagrams depicting how concepts are related, utilized, and they term structural tautologies. Well, in my opinion, the biggest strength of this work is that it acts as a first step, a foundational one, toward reasonable, personalized instructions, where the needs of each learner are accounted for and each piece of isolated material, and is finally contextualized. However, knowledge graph calculation is critical, but it remains labor-intensive. Next step, we need to investigate how large language models can automate the extraction of the tuples when provided a modular ontology as a guidance, which is in many recent work is against it. So that two curriculum ontologies that I present today provide a quite interesting, robust and modular schemas needed to test AI-driven extraction in my current research. And that's all for now. Thank you for your attention.